science at the North Carolina State University. I have known Tiffany for quite a few years now and enjoyed reading her papers on AI-driven learning games, educational data mining, reinforcement learning, models of interactive problem solving. Tiffany is currently the president of the Educational Data Mining Society. She's also a great speaker, so I'm looking forward to hearing what she's going to tell us now. Tiffany, the floor is yours.
Thank you so much, and thanks for inviting me to speak today. I'll share my screen. All right, so today I'll talk about compassionate data-driven tutors for problem solving and persistence. Again, thank you so much for inviting me to speak today. I'm really excited to tell you about our most recent work. I probably haven't shared the slides, but I've got that link there. I will make them available after the talk. So before I go any further, I want to acknowledge that the work I'm presenting is done by a lot of people. This is only some of the people, but the ones who are prominent on the work that I'm going to be talking about today, especially the top three, Mehek Manaktala, Yihwan Dong, and Samiha Marwan, all who have defended their PhD dissertations in the last year. All right, so we're going to start out talking about a problem I went to solve with Mehek, the assistance dilemma. So the assistance dilemma is a balancing problem between information giving and information withholding. You know, anytime we're trying to teach, we don't want to give too much information. We want the students to figure out what they need to do next. But we do want to optimize learning. And if we don't give enough, then a person might not be able to make any progress in solving problems. So one of the solutions that we've looked to do within our tutoring systems for logic especially, and also for programming, is to provide unsolicited assistance. So that's one way of making sure that you give enough information, but it may take away a learning opportunity. But if you withhold it, we might get frustration and reduced motivation, and people might even stop doing problem solving. So within open-ended domains, this can be pretty important to do because students have many, many paths to solve problems in open-ended domains. So we might want to, it might be more important to figure out when people need help in these domains where they might be going in circles and not actually knowing if they're making any progress at all. So the context that we're going to talk about this in is a logic-proof tutoring system, and it's the one that we use is called Deep Thought. It's been in development for many, many years, and I use it in my discrete math class in my North Carolina State University discrete math class. Here's the interface. It's for solving logic proofs. This is called the workspace. On the left-hand side, each of these nodes is a propositional statement and a proof. Up at the top, these are givens. Down at the bottom, that's the conclusion that a student needs to derive. It has a question mark above it because it has not yet been proven. In the middle are the rules that the students are allowed to use. I'm not going to talk about it, but on the right-hand side are just messages that tell the students what's going on. There is a hint button at the bottom. It's called Get Suggestion. And there's a message box for providing hints. And that's how we used to provide hints. Now we actually add nodes to the screen, and I won't talk much about that today, but just putting that hint onto the screen has improved our rate of students using hints and getting hints when they need to get them. But I'm going to focus more on what we've looked to do to see when students are actually making progress, when they are solving problems in open-ended domains. So we wanted to look at that, and we started to research productivity and also when a student might need help. All right, so logic is a well-structured open-ended domain. That means that there are well-known steps that students can take, but there are many, many solutions to the problems that they're looking at. All right, so what we're going to be doing is an extension of my prior work called the Hint Factory, which I used to do data-driven hint generation way, way long time ago. And it takes into account the following to score every step in a problem-solving process using previous student data. So we look to which states lead to solutions, and a state is, you can think of it as a screenshot of what's been done so far in the problem, or back in the day when students did homework on paper, just what is each line that a student put on the paper when they were solving a problem, and which ones of those lead to solutions. So if you're thinking about a student solving a problem, taking consecutive snapshots of what they're doing along the way in that problem solving process, thinking about which ones of those actually lead to solutions. Students might delete work, they might move forward at any given time, and we want to be able to rate those steps every single time as to whether a person is making progress or if they are making too many mistakes and they need help. We want to know how efficient are the solutions that can be reached from a state in a problem-solving attempt. We also want to know how likely a student is to carry out a specific step that we've seen. And my prior work on the Hint Factory, I'm not going to go into the details of these equations, but I can happily provide some papers for you to look at. This is from our JEDM paper on help need. So my prior work actually looked at a whole tree of student solutions, thinking of the start state as a starting node, and then branching into all the different states that we observe, and basically made a reward function for whether or not a step was a given quality by modeling the whole solution space as a Markov decision process. And that's what we call the Hint Factory. And we made a reward function, and that is if there was a state that was a mistake, they got a -10 reward, which is a cost, and taking any action had a reward of -1, and goal states were given a reward of 100. And then we used value iteration to assign values to every single state in our observed states that students ever took in a problem-solving process. And in the most recent work that Mehek did, she proposed this global quality metric, which was looking at not just what is the next best thing you can do at any given time, but what is the best thing across the entire space that we've ever seen students ever do. And in this case, we still had reward function. If you made a mistake, it's still a -10 reward. If the action is taken, it's still a -1 to benefit shorter solutions. And then goal states were given 100 minus scaling, so that the median value of this function is about 80, so that most of the goal states, all the different goals that we could get to, are given at 80. Let me clarify one thing. So within this problem-solving domain, if we look at our tutor, I'm not going to look at it. Within this problem-solving domain, we do know when a proof is solved. So when I showed you that picture of all the givens at the top and the solution at the conclusion at the bottom, the proof is solved when the givens are connected to the conclusion. That means we can automatically detect that. So there are many, many solutions, but we can automatically tell if it's complete because the graph is connected. So you may not have that in your domain. All right. So here's a visualization of what progress we looked at. So efficiency was what we were looking at before, and this is progress. So if you think of all those snapshots as these squares in sequence over time, the current state being the darkest blue one and the prior state right before it, this is relative progress. So how much progress have I made since the last snapshot? That makes a lot of sense. Okay, but you could also think of absolute progress. So like I mentioned before, every time you're taking a problem-solving action, you can compare the current state to the start state to see whether or not you're actually closer to a solution. So maybe you are better than the previous, but maybe you've actually done even worse than the start state. That might happen if you're far off. So if you're doing things that aren't needed for a solution, then you could be very far off. So an absolute progress measure could compare the current state to the start. And that means that if I were to compare two consecutive actions, I could tell if one was better than the other because it would have the difference between the current and the start state would be bigger than the previous step and the start state. So if I wanted to get relative progress, I still could. All right, so we wanted to use these two things, state quality and progress, to figure out if somebody's being productive, because that's what you really, if you think about it intuitively, a person is making progress on a problem solving task if they have high quality steps and they are actually moving towards the solution. All right, so we proposed in this work, I'm not going to focus on the four different things, but using these different calculations, we could figure out how efficient something is, looking at relative progress or absolute progress, and global quality or local quality. Long story short, we focused on global absolute step efficiency, and that was because it was the one that was most correlated with best performance on the post-test in our tutor, but all of these are valid measures that you could use for different reasons. You would use global absolute if you're trying to promote really efficient solutions. You would use local relative, which is what our original hint factory did, if you don't ever want to suggest to a student that they ought to undo any work that they did. So if you think that they highly value what they've done so far, you would use local relative. And if you want them to get really efficient solutions, you would use global absolute. All right, so the next thing we wanted to do is we wanted to say, okay, if we can now classify productive steps, we also want to classify the quality of a step. We want to now classify whether somebody needs help or not. Okay, so we thought about this and we said, hey, this is a combination of efficiency and duration. All right, so we don't think you need help if you're acting like an expert. If you're doing efficient things and you're doing them quickly, that's expert behavior. That's expert-like behavior. You don't need help. That's classified as not needing help. So help need is our classification. It's not ground truth. Just want to be clear. This is not ground truth. We don't have ground truth. We are not looking at every single step a student can do and grading it. It would take a long time. There's thousands of steps that students do and thousands of states. So we don't really want to do that. What we want to do is have a way to classify what we're seeing across what students are doing in problem solving. Now, the next thing we have is strategic behavior. So this is where a student does something that's efficient, but they take longer. That's okay because the student still, maybe they're demonstrating that they learned something. They're not as fast as an expert, but or the faster students. And then opportunistic, we consider this like if you're doing something in a problem solving process and you see something that could be done and it doesn't take you very long, you don't need help. That's just saying, oh, I see that even like, you know, if I go in my kitchen, I pick something up and put it away, even if I don't need it for the next thing I'm doing, it's not, I don't jump in and say you need help. So moving on. So you do need help. And based on the literature, you do need help when you're in an open-ended problem solving domain, if you're far off from the solution. And I'm inspired by, you know, work on database tutors, you know, where and linked list tutors, where if a student, you know, deletes something that they need for the solution, like if you have a linked list and you delete the head node, you definitely need to undo that. So if you're far off, you're going to need some help. Within this context, we said we might want to think about how many inefficient steps in a row become, you know, being far off. Within our domain, we have a lot of proofs could be solved in 5 steps. The average number of steps that students take is somewhere around 12 with a big standard deviation. So 2 in a row, we considered if you're doing 2, then you're not actually trying to think of a strategy to solve the problem. You're just doing things in an opportunistic fashion, but you're no longer acting like you're trying to have a problem solving solution. And then futile is the last category, which is obvious that if someone takes a really long time to do something that doesn't move them forward in the problem solving process, we would call that futile. Not publicly, but in our classification system. Okay, so then we wanted to build a predictor based on our data. So in a previous study, we showed that students could be productively persistent, and we wanted to see if we could predict whether somebody needed help at the start of a step, and then actually proactively give them a hint. And we called those assertions because we gave them what they should derive next, but we didn't tell them how to derive it. So we called those assertions. So we built a 2 classifier architecture. The first one is based on our hint factory work, which is taking all the historical data we've ever seen on problem solving and matching a student state to that. And then state free is when we take all the features of the problem solving process, like how long have they taken. We've got 140 features. This includes like what they've clicked on in the environment, lots of different things like that, whether they got hints or not, and classified help need and built different classifiers. We compared a few different kinds and ended up with a random forest classifier that we used. We did tenfold cross-validation, and we got pretty good recall and AUC for both of our classifiers. So we needed both of those because the state-based classifier is needed when we see a problem-solving state that students we've seen before. So when we get a new student and we've seen that's what their state they're in before, we can classify that very well. But if they're doing something new that we've never seen before, we've got to use all the other features of their problem-solving behavior to build a classifier, and that's what state-free is. So we haven't seen that state before. All right, so then we did an experiment with undergrad students taking the discrete math class in fall 2019. And there were two different conditions. The adaptive condition that had this help need classifier. Whenever they were classified as needing help, we gave them a suggestion for what to do next. In the control, they didn't get that. All right, so within the tutor, there are 4 parts. There's 2 examples, work examples that show the student how the tutor works, 2 pre-test problems, 15 training problems, and 5 post-test problems. And the post-test is harder than the pre-test. We hypothesized that students in the adaptive condition would have better post-test optimality. That means shorter proofs and time than those in the control. And we did find that the adaptive condition, when they got the hints during training, but not in that post-test, they did have better scores with a moderate Cohen's effect size, but a better effect size on the time. So they took only 18 minutes on the post-test in the adaptive condition, where the control took 29 minutes. I can't get my, here. All right, so we can check that hypothesis off as being true. All right, we further hypothesized that students in the adaptive condition would exhibit better training behavior in the control, and they would have fewer steps where they needed help. So let's take a look at that. We compare the training steps between the 2 conditions, and this is with our help need classifier. So how many were expert, how many were strategic, how many were opportunistic, far off, or futile. So we did have in our adaptive condition, we had fewer opportunistic steps. So they're not just looking around for things that could be done. They're also not making as many consecutive inefficient steps. So we did get significant difference in those, but not in the futile steps. So overall, we didn't have a significant difference in the help need steps. Further, we hypothesized that they would have lower possible help avoidance and higher possible help appropriateness as measured using our classifier. So I'll have to give you a little bit more detail on that. All right, so here's how we define our possible help avoidance and possible help abuse and help appropriateness. So help avoidance is what % of the steps are there where we, after the fact, when we look at the quality of those steps, did they need help, but they didn't get any hints, or they didn't receive them and they didn't request them. All right, so if we take a look at that, the blue is the adaptive condition. Those were the ones who got the hints, whether they liked it or not, if we thought they needed help. And their possible help avoidance is lower. So this is what % of their steps were classified as needing help and they didn't get help. So much fewer students in the adaptive condition were not getting the help they needed. All right, when we look at possible help abuse, this is the % of steps with no predicted or observed need for help, but hence were requested. So this is help abuse. This is when students they could figure it out themselves, but they're asking for the help. We had a lot less in our adaptive condition than in the control. And then for possible help appropriateness, this is what % of steps had predicted help need and hence were received. So this should be pretty good for us. And that's a pretty high %. So 23% of the steps we predicted that help was needed and students were given help on those steps. In the control condition, there weren't that many hints requested, so they didn't get that many, and only 4% of the 4.7% of the control group steps were they needed help and they actually got it. All right, so this was confirmed. All right, so looking at the predictor, so our predictor is a prediction of help need, and then we want to see like how does that compare. The main thing that we're looking at here is steps where we predicted, so this pred-HN is like we predicted help need and no hints were given, predicted help need and hints were given, predicted okay, that means they didn't need help and they got hints, very, very low. But here's where we think this is maybe some misclassification. We thought that the student were okay, they didn't need help, but they didn't receive hints. So in our adaptive condition, we had twice as many steps that we thought were okay and students didn't need help, but they actually did. So what does that mean? It means that our help need predictor sometimes thought students were okay, but they actually weren't. And then we looked into our data and we figured out this is actually because when we give students a step that's correct, a hint for something to do correct, they often take that hint and they do it. But that's evidence in our system that they know what they're doing, but the system just told them that. So what we didn't have is a way to account for students getting help within our tutor, within our predictor, so in our classifier. So that was our scope for improvement. So we did add that. So we wanted to address this problem here where we predicted the student was going to be okay, but they actually weren't. They had observed need for help. All right, so what did we think we needed to do? We needed to take into account that the student just got a hint. When they did that really nice optimal step and they did it quickly, maybe it was just because they got a hint. So we built that into our classifier, our predictor, and that improved our signal. And what we did is we penalized the gain in quality and progress by half based on some prior work. So this is just a picture of what it looks like when we do give a hint. So here's what students has done so far. We give this hint, it appears here in the middle as something that they can derive. Once they justify it, that means it's connected to something in the proof. That's called a hint justification. If you look down here, here's the quality and progress scores of this state before the student did anything. They had a global quality of 81 and progress of 7. And if they took this step without our modified help need classifier, they would have gotten a global quality of 87 just for deriving this and a progress of 13. When we penalize because it came from a hint, they only get 3 points for that difference. So the difference between 87 and 81 is 6. So they only get 3 extra points for global quality. And then the difference between this 13 progress and 7 is 6, and they only get half of that, which is 3. So that's how we penalize getting a hint. All right, so we did that training and wanted to build that in. Then we did a study in spring 2020 with an adaptive condition and a control. It was much smaller. We have lots of conditions in our tutor. Same situation. We hypothesized that students would perform better in the post-test than the control with shorter proofs in less time. Let's see, did that happen? Nope, the time was the same and it wasn't really a significant difference in length. They did have better accuracy in the post-test. All right, but during training, did they actually do better? So the answer is yes. So they had shorter proofs in less time, and they had more accurate steps. All right, so we wanted to see how did the predictor, we wanted it to have a lower proportion of false negatives. So false negative is where we predicted help, no need for help, but they actually did need it. So we wanted to, sorry, I'm messing myself up with that. Sorry about that. Okay, lower proportion of false negatives. Let's take a look at what that means. We couldn't look at previous things. So we wanted to compare the 2 predictors on the data set that we were looking at. Let's see. this was the false negatives were where we predicted that a student would be okay, that they wouldn't need help. That was our false negatives, but they actually did need help. And our new classifier had 7.1% of the steps that were false negatives. And that was much less than the fall 19 study, which is what we were trying to correct for. All right, so we confirmed that hypothesis. Then we wanted to see if we improve the predictor. I think we want to skip this part. Sorry, I didn't have time to delete all the slides I didn't want to do. I did want to say we did improve the students' help behavior with this new predictor. So possible help abuse in fall 19 actually was less than in spring 20. What does this say? Well, it says that actually now we had students actually maybe gaming the system. COVID did happen in between these two studies. So we think that the students might have been more stressed, so they might have been using the hints more because of that. We did think that the spring 20 would have lower possible help avoidance than the control. And our adaptive spring 20 adaptive was significantly better than the control and the adaptive and controlled conditions in fall 19. So this means that our new predictor helped us reduce the possible help avoidance. All right, and we thought that the spring 20 adaptive would have higher possible help appropriateness. This means getting help when they need it. So remember, the whole reason for the revision of our predictor was that we had times that we thought students didn't need help, but they actually did. And it looks like we got a vast improvement in the possible help appropriateness when we revised our classification of the quality of steps based on whether a student got a hint or not. All right, so we did succeed in most of our hypotheses, except we didn't save students time in the post-test. All right, so far we've looked at an effective way to incorporate hint usage in modeling help need for this. And we looked at its impact on the predictions for need of help and its impact on students' training and post-test behavior. And it looks like sometimes we might be promoting students to ask for help when they really shouldn't. But most of the time we're not doing any harm, I believe. All right, so that's tying all that up. The next thing I wanted to do was actually peek into some similar work that we tried to take some of these ideas from our logic tutor and look at them in programming. So we wanted to say, hey, if we can classify productivity and need for help in logic, can we do it in programming? All right, so students a lot of the time don't use hints the way they should. And we've tried to take hints from logic and put them into programming. And they often avoid hints in both environments. And students often will need some kind of proactive intervention like we've been talking about. All right, so we want to figure out like when are students struggling so we can figure out if we need to intervene. So we have an introduction to programming course for non-majors. We have traced data from their programming assignments in a block-based programming environment, and it has timestamped student actions like a log for most tutors that you would look at. And they could ask for help in these environments based on this hint factory work that we had done before. The two assignments are called Squirrel and Guessing Game. We have data from 45 students on Squirrel, 50 students on Guessing Game. There's 25,000 actions in Squirrel and 22,000 in Guessing Game. Each of these tasks take about 30 minutes. They didn't use very many hints. And then their average grade is 10 out of 12 or almost 12 out of 12. Squirrel is a homework and Guessing Game is a lab. So Squirrel is to write this code. This is one way to write code to draw this shape. We call it a squirrel because it's kind of like a square shaped spiral. And Guessing Game is where you ask the user to tell you their name and say hello to them. And then you say, hey, guess a number. and you have a secret number and they have to guess until they get it right. You also have to tell them if it's too high, their guess is too high or too low. All right, so here's the intuition for this. We said a student is struggling if they can't make significant progress within a typical amount of time. And so we came up with 4 steps to identify struggling moments in a similar way that we thought about the need for measuring productivity and help need in logic. So we wanted to have a way to measure student progress and how much of it means it's significant progress, and how much is the typical time to make significant progress, and then identify moments where they're not actually making significant progress within that typical amount of time, and we call those struggling moments. All right, and this is relative to the performance of the majority of students. So we used percentiles and 25th and 75th percentiles in our measures, as you'll see. Okay, so the first thing that we did is referring back to work that I did with Thomas Price, and mostly Thomas Price did, it was his dissertation, was an algorithm to take all the previous solutions we had to a programming problem and make a distance metric from what the student is currently doing to all the different solutions that we have in a database. And it's basically how many steps would it take to take the current solution, the current state, and add code to it until it actually matches with the solution that we're considering. So that's the cost. All right, and we match this student state to the correct solution that has the smallest cost to get there. And then the similarity score is the inverse of that cost. All right, so here is a visualization of student progress, which is you take their code snapshot and you compare it to all the different solutions you have, and you calculate the similarity, and the closest similarity is the one you assign it to, sort of like in cluster analysis. And then we plot those similarity scores over time, from where time is going from 0 to however long it is. This is in seconds. All right, and here you can see in the first 2 minutes, there was a period of really rapid progress. And then there was kind of a slower progress over the next few minutes, then actually a time with really not any progress at all. They actually were editing their code here, like rearranging it, deleting some parts and moving them around. Another period of rapid and then a little bit slower progress, and another plateau right before they finished and turned in their assignment. All right, so that's where we have some progress measure because we can compare student solutions to our prior solutions. Then we actually took the maximum similarity score achieved at any given time. So that is, if you look here, it's this red line is this maximum similarity score, which is called absolute progress. And it's the red line here. And it's the most difference here where the student was breaking their code and then fixing it back. But the absolute progress is still here. This is the highest similarity score ever achieved up till now. All right, that's the difference. So progress in between 2 snapshots is the difference between the maximum similarity score they've got at 2 different times. All right, so here's 2 consecutive snapshots where there's positive absolute progress. So you can actually see the similarity score has gone up. Here's a time with no absolute progress. And here's another time with no absolute progress. All right, and then we took all of the progress measures that we had in consecutive steps, and we put them, we rank them in order of the magnitude of that progress. And then the 25th percentile, we say that's enough progress to say that you've made some. So realize that most progress that students had in consecutive steps was higher than this 0.25. So this measure, the actual number doesn't mean much, but it's 1.25 for squirrel and 1.5 for guessing game. So that's the difference in similarity score, absolute progress between 2 steps. All right, so that's like how much is enough progress. So if you're making less than that, you're doing worse than 75% of all of the consecutive steps in your program. All right, so then we said, okay, let's break the series traces of students' programs into chunks. every time it achieves significant progress. So if you think of the whole trace and all the snapshots that have ever been done, there's lots of snapshots in between two of these red lines, which demonstrate when significant progress was achieved. So remember, we've got that 1.25 number. That's that absolute progress. And so we just say, how long is it until we get 1.25, a difference in 1.25 between the max similarity scores we've got. So this is for an example of one student trace. And then we figure out the duration of each of these chunks, like how many seconds did each of these take? And then similar to in step 2, we plot all of the different durations of significant code chunks, and we pick the 75th percentile because we want to give students more time than they might need. So most steps are going to take in Spiral, significant progress is achieved in about 105 seconds, and in Guessing Game, significant progress is achieved in about 85 seconds. And you have to do this separately for every different assignment. All right, so a struggling moment is a code chunk that achieves significant progress, but it takes longer than the typical amount of time. So that 105 seconds for Spiral or 85 seconds for a Guessing Game. And a progressing moment is a code chunk that gets significant progress within the typical amount of time. So you're making progress if you're actually getting that 1.25 mark in Spiral or 1.5 in Guessing Game within the amount of seconds for each assignment. So if you look at it, these numbers, we didn't want these numbers to be super high. So this is good. Struggling moments being 20 to 22% of all of the different code chunks. And most of them progress being made most of the time. That makes sense because the scores on the assignment were not too bad. So the next thing we did was to evaluate this classification, this completely automatic, with some expert ratings. So we wanted to see, we had 2 research questions for this. To what extent do human experts agree with our progressing moments and struggling moments? And what are the common causes? We're not going to look at that one, but we did want to see how much did they agree. So we sampled 20% of the struggling moments from each assignment, and then we took the progressing moments right before those. And then we had 3 experts rate each of these. And this on the right is like a little video of experts looking at a code trace. So they can actually see what's in the programming environment and how it's changing as they scroll through this trace log, which is on the right. It's a trace viewer. And they had some timestamps that they could choose where they could indicate whether they thought that a person should intervene to help the person or not during the struggling moment, and if they're making progress or not for progressing moments. So the green time is that 75th percentile. So we asked them, do you think we should intervene now, or do you think we should intervene at the 65th percentile, which is the yellow? Or should we do it even before that? Or should we do it later than the 75th percentile? Should we do it at the 85th percentile or never? All right, and we had the experts do that every single time. We did ask them to think about being a tutor and whether or not we would be like maybe providing some proactive help or not. We wanted them to think about the time taken, the student actions, and their code correctness, but to avoid hindsight. They weren't supposed to look forward in the student trace, just looking at the data we had gotten so far to decide if an intervention is needed. All right, and then they did some training and they did 3 rounds of independent rating, and each round rated 1/3 of the moments. And then they did a discussion after each round, but they were not required to reach full consensus because the different experts had different ideas about why you might want to intervene. All right, so we merged the 5 timing options into green or before and not yet. So if we go back to this, green or before is 75th percentile or before that. Or they don't think they need help. And then we looked for some common causes for disagreeing. All right, and it looks like we actually had 77% of the time, the raters thought that the struggling moments were correctly needing intervention at the 75th percentile of time or before. And a better rating was given on Guessing Game. For those raters said they agreed with the automatic rating of code chunks as struggling 83% of the time. And we got 85% agreement with progress being made. So the progress chunks were rated as good. All right, so then we looked at when did the raters disagree with the struggling moments. So sometimes there was a weirdness that was happening because of our use of the source check algorithm, where we were matching solutions to a set of possible solutions. And sometimes a student is coding in a certain way and it matches one of our old solutions, and then they switch and their code becomes more similar to another solution we have. And then the similarity metrics may not be comparable. So that might, that sometimes change some fluctuation in the similarity growth over time. And then another reason why some of the raters didn't agree with the automatic classification is that there weren't that many coding actions. So the rater didn't feel like they had enough actions to determine if the student needed help or not. When there was disagreement with the automatic classification on progress, it was because the students might have made a logic error, something that our algorithm isn't doing. It's not actually checking the code for correctness or not, or a human factor, like a human can read the names of variables and tell if someone has made a mistake, where the algorithm can't do that at all. All right, so this method could be generalized to other domains if they have the following criteria. The students mostly have to achieve mostly correct solutions. This seems pretty okay if we assume, bell curve behavior for most classes and many problem-solving domains. So that seems pretty generalizable. If you have trace log data, also seems pretty generalizable. If you have some kind of online tutor where you have students taking problem-solving steps and you can take a trace, you could have that. But you really need a progress measure. So some kind of distance metric that tells you what a problem state looks like and how close is it to a correct solution. So in logic, we did that with all the prior solutions and some reward functions and treating them as Markov decision processes. In this domain, we did a comparison between code snapshots and final solutions. All right, so there are some limitations to this. The raters were not pedagogical experts. They represent highly qualified TAs. They were graduate students who've looked at this kind of data many times. And we had a small sample size. So it's only 2 assignments, and they're also really small assignments. All right, but it's really cool though that we could get such high accuracy with completely just using the data set for seeing how quickly can students make progress and how long does it take to make progress. All right, so at this time, I just wanted to pause for a moment and see if we have any questions or ask the leaders also if we wanted to, how much time you want me to leave for questions or discussion with the audience. Because I have like a whole other thing I'd love to show you, but I'm also want to leave time for questions if you want.
Sorry, I was struggling with unmuting my microphone. We do have one question. I would like to ask all the participants to add questions to the Q&A. I have tons of questions as well. Maybe we can start with Bo's question. It's a very interesting keynote. In the struggling moment study, how did you represent students' code? Was it using abstract syntax trees? How did you measure the similarity between students' code?
Yes, the code is represented using abstract syntax trees, and it was compared with prior student solutions. We usually had about 12 different solutions we were comparing to. It's a little bit like tree edit distance, the metric that we have, but it's been modified to take some things into account because in a block-based programming environment, sometimes the action that you take is like to take a chunk of code and you pick it up and move it. But in the abstract syntax tree, it looks like you deleted it and then you added it again. So you get these huge fluctuations in tree edit distance. So we did some kind of hand wavy stuff. There's some math to it, but it's basically to kind of get rid of some of those snapshots in the middle, those sequential abstract syntax trees to classify something as a move instead of a delete a bunch of stuff and adding a bunch of stuff. So it's pretty much tree edit distance with some minor modifications. That's in a paper that I have with Thomas Price on our first paper on generating hits for programming.
Okay, thank you for that. I would like also to ask a question about that part of your talk. So when you were determining whether someone is struggling or not, you're looking at the average time for that particular problem for all the students. So it's kind of looking at relative to the whole class.
Yes.
I was wondering whether that would work for all cases, because there would be individual differences between students, and you might have someone who is always slow, let's say always takes more time in comparison to the class, but in this particular problem they're actually getting better. So I wonder whether you looked at that kind of possibility.
We didn't do that. So this was a very, this is, brand new work. We just presented this at EDM 2021, and it was a first pass. It's sort of like, if you take Bayesian knowledge tracing and you say, oh, Bayesian knowledge tracing, it's awesome. And then you say, hey, can we improve it with student parameters? Absolutely. Yes, you can. So yes, I think there's plenty of potential for, trying to figure out the sort of set point or the amount of time a student takes on different steps. I think one challenge with that, especially, everybody has this with web-based things, is that people, time is a funny measure with these things because people don't always stick in the browser. So sometimes, a person, might look like they're taking longer just because they go do something in between each things. I have a toddler myself, so, sometimes I'm crazy long on some stuff and really fast on other stuff, and even an individualized parameter might not work. So yes, I definitely think you could definitely adapt this to individual students.
Okay, do we have any new questions? Not yet. Okay, so I'll use this opportunity to ask questions about the first part of your talk. A few years ago, we analyzed data from our tutors, and we noticed, especially in the help abuse class, students who ask for help quite a lot, that there were some students, that was a minority of them, only a small fraction of them, that were actually excellent students. And we were wondering for a while about that. And we then realized that probably what these students are doing is they already have the solution in their head. So they don't want to type it in, to type the whole solution in. They just look at the solution and say, yes, I was right, and they continue with that. So I was wondering whether you have seen something like that in your tutors.
That's a great question. I haven't looked for that specifically in the logic tutor, but it does call to mind an old paper that was, it was Ben, maybe it was Shapiro. I'm probably messing up the last name. There was a study in EDM many years ago that looked at sometimes students are using bottom out hints as worked examples, or, like you're saying, you've got some students who are almost experts, right? And they were just kind of being lazy, right? They're just checking their understanding. And if they are fine, they're moving on. And actually, I think that's a great use of their time, right? So that's not really help abuse, is it? It's actually, no, it's not. It's effective time management for those students. So I think that's definitely interesting. So our focus in this work has been, if a student needs help, let's give it to them. So none of this would prevent a student abusing help in that way in our system, but we were using our help need classifier as a, kind of, it's not the ground truth. It's the only way we know to kind of have some kind of measure whether somebody needs help, and it's sort of classifying the quality of the steps that they're making. So if a student was doing like that, they're asking for help and then they do what the help says, those students might still be classified as experts, because even though we penalized getting help, they still had a high quality step. So those students would still have actually pretty high metrics, and they probably wouldn't get automatic help popping up.
In our case, such students typically did not complete the problem. They just look at the solution and then they abandoned that problem and went to a different one. So I don't know whether students can do that in your tutor, or do they have to complete each problem before going to the next one?
They can skip problems, but they do have to finish them. And when they get a help, like when they get a hint, it doesn't do the step for them. So ours is just, it tells you what you should do, but you have to do some stuff to actually
complete it.
Do it. So you have to click on two things and maybe type something. So it doesn't take long. So they could finish the proof faster if they did that.
Okay, we have another question. How can you identify the moment when students are taking offline, if they're drinking coffee or something, not really working on the problem?
We do that in both of our tutors. Anybody who's got, log-based stuff usually does looks at a histogram of how long it takes for consecutive actions. And if something is longer than the, 95th percentile or whatever, you just cap the time at whatever that is. So that's what we do. In both of our systems, we're capping the time. So we're just assuming that they went to get a coffee if it's longer than typical. By the way, most of the steps in the logic tutor take 30 seconds, and most of the steps in programming take less than 2 minutes. So a lot of them also take about 30 seconds. So if somebody took 5 minutes, 5 minutes is our absolutely, we never record any time, we record it, but we don't use it after 5 minutes, but we usually use a lower cutoff depending on what the histograms look like. That's definitely important.
There is another question. Is the progress analysis real time during programming? Is it possible to predict students' progress dynamically so that a teacher dashboard can be developed?
Yes. So this method that we did for the programming, all of it was done in a way that could be done automatically. So using the using this progress measure. So SourceCheck was developed so that we could do real-time hint providing. So we could actually match the student solution to the solutions that we had and choose a hint. All that's done in real time. So everything we did in this study could be done in real time. We haven't done it in real time. This was a retrospective analysis to see if our sort of, back of the napkin calculations using percentiles would actually give us a good rating. And I think it does. And this is what we've been struggling. We've been trying to, I don't know if you've been following our papers in educational data mining, we've been trying to use fancy models to classify student behavior in programming to see if they need help. And, basically we cannot, we can tell if somebody's expert. So what, if you want to look at our papers, they're good papers and we did some cool machine learning stuff, but what it really tells you is you can tell if somebody kind of knows what they're doing in the first minute or two of doing one of these programming assignments, and then they never need help. And if they're not doing good in the first 2 minutes, they mostly need help. So they're not very good. That's why we wanted to use something like this, because there's so much diversity in student solutions and it's extremely hard to tell when somebody needs help. So we thought that the time that people were taking and, some kind of progress measure would give us a nice first pass. And I think we really do want to do this in real time. So we really tried to make the study in such a way that everything that was calculated could be done in real time. Of course, our experts can't rate things in real time, but now we're saying, hey, this is good enough accuracy. So I'm usually trying for approximately 80, I like to solve 80% of the problems for 80% of the students, with quick and dirty methods. Let's get it in the system, let's get it working, and then let's fix the parts that aren't working too well.
Thanks for that. A few more questions about the help need predictor. So in the studies that you performed, students had a single session, right?
Students could work on those problems whenever they wanted, so they can log into the tutor, log out, okay. So everything's just logged. More than one session, however they want, they were homework.
Is it possible for a student to ignore the hint?
Absolutely. So the picture I showed you. So with our help need model, when we pop the hints up on the screen, the assertions that stick right on the screen, they adopted those hints 93% of the time. And if they asked for a hint, those same students who were getting those automatic hints when we detected that they needed help, they used them 93% of the time. And when they asked for hints, they used those 95% of the time. And then students who didn't get the help need models, the control group students, of course, they didn't have any that popped on the screen, but when they asked for help, they only used that help 85% of the time. So the ones who were kind of getting help frequently were more likely to use it, and then were more likely to request it and then also do what the help said. But the control group students, there's still 85% is pretty high. So before we did this, putting it on the screen, adoption rate was about 65%. So we just would put a little message at the bottom when we thought they needed help, and nobody read that, basically.
We do have another question. Is the reinforcement learning technique used instead of supervised machine learning model?
So yes, the random forest classifier was using supervised learning. Well, let's see, we were feeding in features. It's probably supervised. So we used random forest on the help need classifier. The prediction was using random forest, using all the features in the tutor. Yeah, I'm pretty sure it's supervised.
Okay.
This one on the programming is it's not supervised. So well, I mean, I guess this isn't really machine learning, but in a way it's kind of supervised because we're using that metric for quality.
Yep. You mentioned that there were quite a few features that you used for the predictor. Was the problem complexity one of them?
No. So our problems in our tutor are, well, actually, yes, it is. We do have a little bit of one, but we don't have like a good, one of the reasons why I do this research is that we don't have like a good knowledge model for logic proofs or for programming. Like we just don't know what knowledge components there are or like really how hard the problems are, but there's a proxy for it, which is how long is the shortest expert solution that we know about. And we do use that. So we do use the sort of that, and we use also sort of like the average number of steps that students take to solve it, which is usually much larger than the expert.
Yeah, so it's kind of based on the amount of time taken.
Yeah, it could be, time taken and total time in the tutor, and those are definitely features that are used. And then you could think of difficulty as like how long does it, how many steps does it take to solve this?
Okay, thank you very much. We are out of time. I would like to thank Tiffany for an excellent presentation and for providing additional explanations to the questions that were raised. We do have a certificate for you, which is going to appear on the screen in a moment. I guess you have to stop sharing first. Yep. And then we should see the beautiful certificate. And you should imagine me giving the certificate to you. Thank you very much for giving us your time. We really enjoyed your keynote.
Well, I enjoyed being here. Thank you so much.
Thanks a lot.
Okay, next, may I invite Professor Ramkulat Rajanadran to introduce our theme-based speaker. Please welcome. Professor Ramkumar, are you here? Okay. Alex, are you here? Could you please help? Ramkumar could not turn on her camera. Can you turn on your microphone? No? No. Please wait for a few minutes so we help you to contact with our technical team. Ramkumar, try it again, please. I think you can.
Hi, thank you. I'm sorry. So I joined as an attendee. so I was not able to turn on my camera and join you.
Okay, so now it's your floor to introduce our theme-based speaker.
Yeah, thank you. Thanks everyone for joining this theme-based speaking. And for today's theme-based Keynote speaker, we have Professor John Manson with us. And John Manson is not a new face to ICC, and we almost know that John Manson associated with APSI for a long time. Dr. John Mason is an associate professor in education in the College of Indigenous Futures Education at Charles Darwin University, where he lectures in the broad area of digital technology in education. He also holds adjunct positions at Korea National Open University and East China Normal University. He joined Charles Darwin University in 2012 as a director of e-learning for Center for School Leadership, Learning and Development, and pursuing an earlier career at the nexus of government digital services, education, and international standardization. Since 2000, John has led delegations from Standards Australia to ISO, IEC JTC, or SC36, and he has performed editorial roles for international projects, journals, and books. John was editorial for Orbital APSI journal for a period. He is an elected member of the executive committee of APSI and serves on several journal editorial boards. His research encompasses most things where digital technology and learning intersect, while also pursuing a keen interest in question formulation, sense making, and role of wisdom in education. Today, John will talk about questioning and digital environment. John, welcome you to start your speech.
Thank you very much, Ram Kumar, and it's lovely to be able to follow Tiffany. I really enjoyed Tiffany's keynote this morning. And yeah, so good morning, everybody, and good afternoon, maybe if you're somewhere else in the world, good evening, all of that. I'm very pleased to be here today to talk about this theme that has interested me for quite some time, questioning and the digital environment. Let me just share my screen and I'll get some slides here for you. Okay. All right, so questioning and the digital environment. Here we go. So one question that has been with me for quite some time now is this: in what ways can we use digital technology to scaffold questioning? But just as a warm-up, just to get going, I've also just set up a little interactive thing that we can all just participate in, and I wouldn't mind just taking a moment to encourage you to hold your phones up to this and see if you can participate in this short little quiz that I've just set up in Slido. I'll just give you a minute to do that. And while I'm doing that, I'll just share my other screen. If I get to it. A moment. Okay, so we'll just share that for a minute. Okay, so looks like there's at least one person. I'm not quite sure how many people are engaging in the poll just yet, but it looks like there's some interest in escaping to the paradise hideaway. Most people are choosing to answer this question, happiness all stations. That's pretty encouraging. That's probably the one that I would choose. Anyway, I'll just escape from that again, stop sharing that and go back to my slides. Okay, so that was just a little interlude to show you an app that I use sometimes. It's got another facility. If you look at it either on the web or on your phone, if you've downloaded the Slido app, some of you may be already familiar with this app. There's a Q&A function attached to it as well. And so if you look closely beyond the poll there, and you'll see an opportunity to type in a question that might matter to you at this particular time, where we are in this new era that we're emerging post-pandemic, hopefully. But in terms of digital learning, what we can do with digital learning, I'd be really interested to have you think about that topic throughout this session. And if a question comes to your mind, please just put it into that form there, and we might review those questions later on in the presentation. Okay, so then to connect with that question of mine, I begin with this idea of ICT, and we all know what ICT means. It's the information and communications technology. But there's an assumption that we probably all have too, and that is that ICT is fundamental to digital learning. There's another assumption, and that is an assumption that I have, and that is that questions and explanations also drive learning. And so I have another question. And my other question is this: why then, if questions and explanations are so important to our sense-making and understanding of the world in our own learning, why don't we have some kind of question technology, some kind of domain of question technologies or explanation technologies for that matter? Why don't we have these kinds of tools with us? If we put in the term question technology in Google, it's quite an interesting thing. Google thinks when I'm putting in these two words that I'm probably looking for Heidegger's famous work on the question concerning technology. So Google's sort of imputed that I'm an academic and I'm likely to be looking at that. Maybe you've got different experience when you put in question technology into Google. You can also get this if you look further down if you put quotation marks around question technology. This is the sort of thing that comes up. Technology is the answer, but what's the question? Okay, so this idea that questions are always coupled with answers. I also actually put in question technologies into Google, and recently came across this website, question.com, and it's run by a company in the US called Question Technologies. And so when I found this, I thought this is quite interesting. This lines up with my interests in what could be possible. And I had a good look at this website, and I thought, wow, this does look promising. It looks like it's driven by social media and all of that kind of thing. But as I dug into it and had a look around, it tended to be, the experience I got from this was really just yet another social media Q&A website. It's okay. It takes things beyond the fast food inquiry experience of Google and gives us an opportunity to have dialogue with somebody or with others, with a group of people in relation to a question that we might have. But there's a lot of these Q&A kind of services around that have leveraged social media over the years. I've sometimes used Quora, I sometimes use Reddit, and quite a bit I use ResearchGate. I find ResearchGate quite a useful tool for an academic, a great way to provide another channel for exposure of papers that you might write, or to connect with others who might be researching in similar areas. So all these kinds of social media apps are really, they each have some kind of value proposition going for them, and this is why people flock to them and why people use it. But when we look closely at how questioning is conducted and supported by these apps, overwhelmingly, what we find is we have a Q&A kind of an experience. Questions, the assumption is that questions must beget, must propagate, must demand an answer. Okay, and I think that one of the reasons why this is the case is because we've come up through schooling systems whereby we're all schooled to think in answers. When the teacher asks a question, I guess, I have to answer that question. So all the kids, right from the early years, are trained, are schooled to think in answers. We're not really schooled very well to think in questions, and that's what I'm particularly interested in. How can we find tools? How can we design tools to help us think in questions? So there's these other services out there. Use Response is another one. It's a service that helps you build a Q&A service into your own enterprise portal or organisational portal or what have you. A bit of a business take on this quest for bringing in user interaction and Q&A into the services on your website. So then, in my teaching, and a lot of my teaching is focused on working with trainee teachers, working in the K-12 space, and my teaching is all about the use of digital technology in education, in the classroom. And I sometimes give a potted history, a shorthand history of the web based on my own experience. And I sometimes summarize it in these three key ways, that there are three key kinds of technologies that have shaped the web to what it is today, and they continue to shape the web. And overwhelmingly, search was the first technology that did that, and it did that long before Google arrived. Google arrived on the scene about 8 years later, but of course it's the dominant player now. But search is the overwhelming technology that helps us organise our thinking and organises our inquiry in many ways on the web. But what it does in terms of questioning is that it abbreviates questions into keywords and key phrases. And even if you put a question into Google, it's a bit hit and miss as to whether it can handle it or not. And then we've got the social media revolution, and latterly in recent years we have this, the emergence of smart learning, the emergence of the smart classroom, the emergence of smart cars and smart fridges, and everything smart is coming along the way. And in a way, and sometimes I characterise these in terms of three different forms of information, of IT: information technology, interruption technology, and intelligent technology. So then back to my question. It's interesting, I took note of an article that came out way back in 2015 by Michael Nielsen, who did his PhD in quantum physics, or quantum computing, I think it was, and a very, very interesting article all about the emergence of computer-aided explanation. And when I first saw this title of this article, I thought, wow, this looks like it's going to be interesting to me. Because there was a proposition in it and a very good explanation in it, all about how the emergence of big data, the volume of data that we now have in our world and at our fingertips, it enables statistical processing in novel ways. So in the past, where we had language translation systems based around linguistic structures, what we can now do with language translation is use statistical methods in terms of the proximity of words, and there's lots of inference that can happen as a consequence of this. And so this looks like an interesting development to me in terms of computing power driven from big data. Pretty much at the same time, there was a book that came out by Victor Mayer Schoenberg and Kenneth Kukier, all about the big data revolution, and it actually had a proposition within it that I found a little bit alarming when I first came across it. I still do find it a little bit alarming, in that they had demonstrated in several experiments how they could build predictive models that could explain certain phenomena that were basically just based on the aboutness of information, based on the what, not on the why. So in a way, the proposition, the big proposition coming out of this book, that reasoning, we could almost do away with the why, moving into the future with the kind of computing power that we now have. So then, connecting all this with some more contemporary developments, I also have an interest in AI, and I came across this report recently from Stanford University. I think it was only published about 6 weeks ago, two months ago. The 100-year study on artificial intelligence, and I thought, gee, this is all going to be very informative for me, learning about the current state of AI, where we're going with it, what are the things we should be asking about it. And so they have this list of standing questions that are there. There's 12 of them, and they're all very important questions, there's no doubt. And this has been driving this inquiry at Stanford for some years now. They update this report, but this is the current state of it. And so these 12 standing questions look to me very, very interesting, how we can interrogate AI. And I look at these questions, and it occurs to me when I look at these questions that even though they are important, what are the most promising opportunities for AI? What are the most pressing dangers of AI? There's the upside story, there's the downside story, blah, blah. If we look through all these questions, we can also see in the structure of the questions themselves that these questions are about procedural or declarative knowledge. There's no questions there about conditional knowledge. There's no questions there about context or why. And so I find this fascinating that researchers who are so immersed in such an important technology of our time are preoccupied with the declarative and the procedural questions. So that's just one thing that a comment along the way I have. So here's a question about AI. Also just came out in a magazine the other day or a website, actually, Forbes. What happens when AI falls into the wrong hands? This is a great question. This is an important question. We should be asking this question, and we should be wondering, well, what other questions might emerge from this? How can we look into that in a deep and probing way? And I think one of the ways we might look into such questions in a deep and probing way is not to be finding answers too quickly in a search and find kind of way. So then, I did mention this before, the phases of web development, the 3 phases. I sometimes think there could be a 4th phase that we're entering into, and this is partly driven by this misinformation age that we've moved into, and partly with the way that social media has evolved in recent years, and how we have a toxic and a kind of a tribal culture quite developed in quite a profound way in social media, and how we've kind of also emerged into this era of post-truth, where opinion seems to trump truth and fact. So this is a question for me: are we in fact at the precipice of a new phase of web development? Where are we going with all of this? So this is a kind of question that occurs to me and that bothers me. So, okay. But here's another statement that links up with my work and my teaching, and that is to do with literacy. And some of you may know of Alvin Toffler. I was going through my undergraduate years when I first came across Alvin Toffler, and he published a book called Future Shock. He's still around, and this is a quote from him from not so long ago: "The illiterate of the 21st century will be those who cannot read and write, but those who cannot learn, unlearn, and learn." And looking into this idea of learn, unlearn, and relearn, there's another report that's recently come out from the OECD that's a futures guide, if you like, from the OECD about where we need to focus our attention as educators. And it's very, very interesting looking into this. We can see into this, in this part of the diagram, if we go into it closely, we can see that, yes, literacy and numeracy are still pivotal to education and learning, but isn't it interesting to see that we now have data literacy moving into this space, and how important it's going to be going forward. Okay, changing pace just for a moment. So in terms of a bit of an explanation of my research agenda, before I moved into becoming an academic back in 2012, I'd been working in the international standardisation space and government services space, and I was working with people in libraries and people who are immersed in information science and developing metadata standards. Metadata to describe internet resources, metadata to describe learning objects, and that kind of thing. And so part of that exercise was all about looking at the primitives of information. And so way back then, it became very, very clear to me that and others around me that when we're developing metadata, the primitives of information retrieval are all about who, what, when, where information. Whereas we do have these other questions we ask when we're trying to make sense of the world and we're querying the world, and we use these, the journalist questions, so-called journalist questions, because we can build stories when we're including a why and a how. I first started to try and model this space some years ago, my interest in it, because particularly the why question here. And that's just an example of how I went about modelling things, trying to distinguish between information and explanation, and how these two things are very, very, very different. But we deal with both when we're learning, when we're making sense of the world. So if we're dealing with both, why is it that all our tools are overwhelmingly based around supporting information and information processing? So then, moving on, modelling this even a little bit deeper, this idea of inquiry, sense-making and learning, I dug in and I've tried to model that, and tried to distinguish between questioning and search. And this has been a model that I've worked with for some years, but still am wanting to take forward. So then I'm just conscious of the time now. I think I've only got about 10 minutes now, including questions, so I better move it along. So then here's another thing that I found interesting along the way, that when we start to consider cross-cultural perspectives on this, we can find some other interesting aspects about learning. And in one of the Chinese characters, there's many Chinese characters that can represent knowledge, but at least one of them is this, where knowledge is depicted as a combination of learning and questioning. Other models we might come across when we're thinking about knowledge and learning and information. We might come across these kinds of representations, and this is one of the better ones that I've come across. Often we see hierarchies where we see wisdom on the top of a pyramid, which I think is a misrepresentation of the relationship between data, information, knowledge, and wisdom, perhaps, because more and more and more I see the value proposition in the world that we're living in, or the big questions emerging. It's all around the data. Data is the centerpiece, really, as the way I'm starting to see things in the digital world. And so here's another representation that I've been developing with my colleague here, Dr. Khalid Khan, who's an expert in mathematics education. And we've been engaged in some dialogue for quite a few years now, and this represents our latest synthesis about that issue of data literacy and how we might go about thinking how to position it within the curriculum going forward. And of course, you can see the place of questioning and sense making there. The way we represent it there is down at an intersection between mathematical thinking and scientific inquiry. So moving forward, I guess as a comment, many of these I put these slides together in a fairly eclectic kind of a way because really the research agenda I'm pursuing is a very open one, and I just wanted to share some of the key aspects of that research agenda. And I'm sharing this particular slide and this book because it had a big impact on me about 15 years ago when I first saw it. And I've within this book, this book is focused on this one technique, learning about the question formulation technique, which is all about flipping the classroom dynamics, which are typically teacher-led. The teacher always asks most of the questions. I'm interested in turning it around, so the students ask most of the questions. So this is a great book for learning how to actually bring about that change in dynamics. And it's also been a book that's helped me think about, well, how can we also consider the design requirements of tools on the internet that then might help us scaffold our own questioning. And so this is another phrase that Khalid and I have been talking about for some years now, the big difference between thinking in answers. When you see your students thinking in questions, you see a very different thing happening compared to when they're thinking in answers, trying to come up with the answer, trying to be first in class, best in class, trying to provide the answer. Thinking in questions is very, very different because it's not necessarily about the best question either. In the question formulation technique, I'm often at pains to emphasize that in many respects, all questions are equal. We often hear people say, oh, that's a good question. Yeah, that's a great question. And often it is a good question in the context, but I've come to the view that where learning is concerned, in fact, all questions are equal a lot of the time, particularly if we're trying to nurture student agency in the asking of those questions. So then here's a question that I noticed in my feed from the New York Times this morning. It's not the most riveting question that one will come across. But it's a question. It's a question that I thought is very pertinent to the sort of field that we're all engaged in. You know, what's one of the most dangerous toys for kids? That's the internet. So I haven't yet watched that video, but some of you might be interested in that video. So then, look, that's my eclectic collection of slides, and so I'm very, very interested to know if anybody has any questions about what I've said this morning, following all of that. Okay, so I'll just stop sharing that, and then we'll see what's happening. So, and I'll just
Thanks,
check my,
John. Thanks.
I'm checking my Slido as well, and it doesn't look like anybody's asked any questions on the Slido, but I am interested in questions now. So,
Okay.
Please.
So, audience, if you have any questions, you can post in the chat or in the Q&A section. If you have questions, John, I have a couple of questions.
I'm sure you do.
The slide up.
Yeah.
Yeah, so
it's your role, Ram, to have some questions now. So you have to do that.
I like the slide on sense making, a concept map you created, and I just would like to know how this concept map has been created. Like, so you had a concept map saying that sense making, the inquiry drives the sense, and that drives the asking the questions. How is this map, formulated? Is it existing literature? Are you? I just like to know more about that.
I used a free tool called CMAP. CMAPs, I think it's CMAP. If you just do a search,
I'm more interested in. I'm more interested in how this. How's that validity? I'm like, is that map come out of from research literature, or have we tested any empirical studies to support it? I'm just interested in that part.
Okay, so it's come out of my own research, Ram. I'll just put it up there again if you like.
Yeah.
I'll just share it while I'm talking. This is the one. Yes.
Yeah.
So in a way, so this particular formulation, this particular mind map was a result of many iterations. I didn't just all of a sudden create it, but based on all what I'd read and all the information and research that I'd done. It was a process that took me some months to map out. I knew that I was interested in the construct of sense making, and I knew that sense making was a very powerful construct, very different to meaning making. I often find meaning making as overdone in educational literature, because we don't always, we're not always looking for meaning, and we're not always trying to create meaning. We're often just trying to make sense of the world. We're just trying to understand things. And so sense making, I see as really an important activity that we need to understand. And if you look in the sense-making literature, there's many variants of it academically. You'll see quite a strong amount of literature, a lot of literature about sense-making in the human-computer interface domain, and you'll also see it in organizational development and also in information science. There's different ways in which sense making is understood. So for me, when I created this, was really about the constructs, the concepts and the constructs that I was seemed to be important to me in the way that I'm modeling my research agenda. So this is all that this is. It's just a model. In fact, it's a sense-making model itself. That's all it is.
Thanks, John. There are a couple of questions from audience. The one is from Rachel. Could you share further on differences you found between thinking in questions versus thinking in answers?
Okay, so sometimes, just as an example, when we use Google and we're just doing a quick search, and sometimes we do just want to find some quick information. Where's the closest pizza place, or where's the hairdresser, or whatever. Sometimes we just want quick in and out information, and so yes, answers are important to us. But sometimes if we're pondering a question like why are the Israelis and the Palestinians locked in such deep conflict, do we think one answer is going to solve our curiosity on that? I think there's probably many questions that we need to immerse ourselves in to gain a better understanding of such questions. And so there are many of these kinds of questions. You could call some of them are wicked problems of the world. You know, why have we still got so much poverty? Why are so many kids not in school? There are these big problems of the world, wicked problems. But I sometimes think that getting to solve some of these problems is going to be a quest that's based around questioning. It's not going to be based around trying to find quick in and out fast food answers from Google. So you know, and again, just to emphasize, you know, I think my own schooling experience was all about learning how to think in answers for the teacher. You know, I'm always trying to get the right answer. And exams are always often geared around the right answer. And so I think, you know, there's an implication here in terms of how the curriculum itself in the schooling system is structured.
Thanks, Professor John. Just one more question about the concept map, where from Mr. Yan, where is the knowledge transfer fit into that particular concept map model? So the concept map had a sense-making inquiry. Where's the knowledge transfer fits in that particular map?
The knowledge transfer, I'm not quite sure what I understand is the assumption behind that question. What I can say though is that when I did this particular model, I also looked at a range of different ways of modelling knowledge, and there's so many different ways of modelling knowledge. Whether we think about procedural, declarative, and conditional knowledge, or you know, if we think about Bloom's taxonomy. So many models in the educational space that help us think about knowledge. So knowledge transfer. This particular map of mine was really, as I said before, it was all about trying to make a connection between the process. Maybe it's the process of sense making. Okay. So in sense making, there's knowledge embedded in sense making, whether it's knowing that or knowing why. Okay. Or yeah.
So I think the clarification of knowledge transfer is application of knowledge in a real world problem. So I think that's what Mr. Yan means by knowledge transfer.
Okay, so we have this real world problem of, you know, why are there, you know, hundreds of millions of kids out of school when we have so much wealth in the world? You know, there's a real world problem. You know, and I need, you know, a lot of us around the world try to make sense of that problem. And you know, how do we make sense of that problem? We need to ask questions about that problem. How else can we dig in to that problem? How else can inquiry proceed if we don't ask questions? We need to formulate questions in order to dig into a problem. And so, in a way, questions, once we really get engaged in research and deep inquiry, our questions are propagating more questions rather than propagating answers as such. So in a way, I sometimes visualize a tool, like a question engine, whereby questions propagate more questions that help us in our research.
Thanks, Professor John. I think we are running out of time. I think we are already 3 minutes over the time. And thanks for a wonderful session. And I guess in the recent days, most instructors started exams in terms of creating questions. They ask the students to come up with a set of questions instead of answering set of questions. So this is really interesting because this throws some light about how to ask questions and thinking about questions. Let's thank Professor John for a wonderful session. Now, I think the certificate of appreciation will be shown here. It's a virtual certificate, and thank you for your contribution.
Thank you very much, Ram, and thank you for everybody for staying with the session. And if anybody's interested in contacting me about anything I've talked about today, please do so. I would really appreciate any engagement about these issues with anybody. Thank you.
Thank you very much. And for your information, apart from attending the conference, there are other activities that you shouldn't miss. This year, we have a fun activity for you to join in order to get the souvenir from Thailand. We call this activity social activity. To join this fun activity, please visit our Facebook page and watch 2 video clips of Thai culture. Then post your comment below that post. The most impressive comments will get the special souvenirs from Thailand, which will be announced at the closing ceremony. Another interesting activity is joining the social love area, where participants can chat or discuss with other participants anytime during the conference. In addition, the Air Meet is used for poster session, where participants can view interesting posters virtually. And for the afternoon session, in this conference hall, you will meet our keynote speaker, Pierre Delingberg, at 1:30, and our theme-based speaker, Baltasar Fernandez mentioned at 3:40. So please join us again in the afternoon session to meet this special speaker. Ladies and gentlemen, this is the end of the morning session in the conference hall. I would like to say thank you to all participants for joining us. See you again in the afternoon session. Thank you and สวัสดีค่ะ